Data modeling is the foundation for unlocking the power of your data. By strategically designing your data infrastructure, you can uncover hidden insights and make more informed decisions. A robust and scalable data model allows you to optimize your business processes and drive greater efficiency. The data visualization dashboard on this slide showcases the kind of insights and analytics you can achieve through effective data modeling. Data modeling may seem complex, but the benefits are immense: improved decision-making, streamlined operations, and a competitive edge in your market. Data modeling is the process of creating a visual representation of an organization's data. It involves defining the entities, their attributes, and the relationships between them. This provides a blueprint for building a database and understanding the data. Data models are essential for ensuring data consistency, integrity, and accessibility. They help organizations understand their data, identify dependencies, and establish standard definitions and relationships. There are three main types of data models: conceptual, logical, and physical. Each model serves a specific purpose and provides a different level of abstraction for understanding the data. Data modeling is crucial for creating an optimized data structure that aligns with business requirements. It ensures data is organized logically and efficiently, improving accessibility and reducing redundancy. By defining data entities, relationships, and constraints, data modeling promotes data integrity and accuracy. This leads to higher quality data that can be trusted for critical decision-making. A robust data model serves as a blueprint for database and application development. This reduces development time and costs as the data structures are predefined and understood by the entire team. The three main types of data models are the conceptual, logical, and physical data models. The conceptual data model provides a high-level, abstract view of the data requirements, focusing on the key entities, their relationships, and the overall information architecture. The logical data model is a more detailed representation of the data requirements, defining the entities, attributes, and connections between them, independent of any specific technology or database implementation. The physical data model is the most detailed and technical representation, specifying the actual database schema, including tables, columns, data types, and indexes, optimized for the chosen database management system. These three models work together to capture the data requirements at different levels of abstraction and detail, supporting the design and implementation of the database. The conceptual data model gives a high-level, abstract view of an organization's information requirements. It focuses on defining the key entities, their attributes, and the relationships between them. Without getting into technical details, this model serves as a communication tool, allowing business stakeholders to understand and validate the overall data architecture. It lays the foundation for more detailed logical and physical data models that will guide the actual database design and implementation. The conceptual model provides a common understanding between the business and IT teams about the core data entities and how they are connected. It helps ensure that the eventual database design aligns with the organization's fundamental information needs. The physical data model specifies the actual database design, including tables, columns, data types, and relationships. It translates the logical data model into a format that can be implemented in a specific database management system. The physical model focuses on improving database performance through techniques like indexing, partitioning, and denormalization. It considers hardware and infrastructure requirements to ensure the database can efficiently handle the expected workload. The physical model addresses data security, access controls, and governance policies to protect sensitive information. It defines database user roles, permissions, and audit trails to ensure the integrity and confidentiality of the data. The physical data model specifies the actual database design, including tables, columns, data types, and relationships. It translates the logical data model into a format that can be implemented in a specific database management system. The physical model focuses on improving database performance through techniques like indexing, partitioning, and denormalization. It considers hardware and infrastructure requirements to ensure the database can efficiently handle the expected workload. The physical model addresses data security, access controls, and governance policies to protect sensitive information. It defines database user roles, permissions, and audit trails to ensure the integrity and confidentiality of the data. Entity relationship diagrams, or ERDs, are visual representations that show the relationships between the different entities or data elements in a data model. ERDs provide a clear, comprehensive view of how data elements are connected and how they interact with one another. They help identify the core entities within a data model, such as customers, products, or orders, and define the attributes that describe each entity. This lays the foundation for building robust, scalable database structures that accurately reflect the real-world complexity of the business domain. ERDs can capture intricate relationships between entities, including one-to-many, many-to-many, and recursive relationships. This allows data architects to design data models that accurately reflect the real-world complexity of the business domain. Data models define different types of relationships between entities, such as one-to-one, one-to-many, and many-to-many. These relationships are crucial for understanding how data is connected and how it should be organized within the database. Cardinality refers to the numerical relationship between entities. Cardinality specifies the maximum number of instances of one entity that can be associated with a single instance of a related entity. Understanding cardinality helps ensure data integrity and consistency. Normalization is the process of structuring a database to reduce redundancy and improve data integrity. We'll cover the key normal forms: 1NF, 2NF, and 3NF. 1NF eliminates repeating groups and ensures data atomicity. 2NF removes partial dependencies to enhance data integrity. 3NF gets rid of transitive dependencies for further data integrity improvements. However, sometimes denormalization is needed to optimize performance by reintroducing controlled redundancy. First normal form, or 1NF, is a fundamental concept in database design that ensures data is stored in a structured, consistent manner. It establishes the basic requirements for a relational database table, including that all values must be atomic or indivisible, and that there should be no repeating groups within a table. Atomicity means each cell in the table must contain a single, indivisible value with no internal structure. No repeating groups means the table must not contain any repeating columns or arrays of data. Adhering to 1NF creates a normalized data structure that is highly efficient, scalable, and avoids data redundancy. This lays the groundwork for higher levels of normalization and more sophisticated data modeling techniques. Second normal form, 2NF, is a database design principle that builds on the first normal form, 1NF. It addresses the issue of partial dependencies, where a non-key attribute depends on only part of the primary key. Partial dependencies can lead to data redundancy and update anomalies. To achieve 2NF, we need to identify and remove all partial dependencies. This is done by creating separate tables for each set of fully dependent attributes. Separating the data this way helps eliminate redundancy and improve data integrity. The key steps are: 1. Ensure the table is in 1NF by eliminating any repeating groups. Then 2. Identify and remove partial dependencies by creating new tables. Third normal form, 3NF, is a powerful database design principle that helps eliminate data redundancy and improve data integrity. It states that a table must be free of transitive dependencies, where a non-key attribute depends on another non-key attribute. The key requirements of 3NF are: no transitive dependencies. A non-key attribute must not be dependent on another non-key attribute. No partial dependencies. All non-key attributes must be fully dependent on the primary key. No repeating groups. There should be no repeating groups of data within a single table. This detailed database schema diagram illustrates the relationships and dependencies between tables in 3NF, with clear labels and annotations explaining the key concepts. Voice code normal form, BCNF, is a higher level of normalization that builds on the third normal form, 3NF. BCNF aims to eliminate certain types of data anomalies and dependencies that can still exist in a 3NF design. The key difference is that BCNF requires every determinant, attribute that uniquely identifies a row, to be a candidate key. This ensures there are no partial or transitive dependencies, making the database more robust and scalable. BCNF is considered the fourth level of normalization, building on 1NF, 2NF, and 3NF. Achieving BCNF ensures a database is completely free of update, insert, and delete anomalies. The star schema is a common dimensional modeling technique that organizes data into a central fact table surrounded by dimension tables. This structure enables efficient data querying and analysis, making it ideal for data warehousing and business intelligence applications. The snowflake schema extends the star schema by normalizing the dimension tables, creating a hierarchical structure. This approach can lead to more complex models, but can also improve query performance and flexibility for certain use cases. Fact tables contain the numeric, quantitative data that is the focus of analysis, such as sales figures, website clicks, or patient records. Fact tables link to dimension tables that provide context and descriptive information about the facts. The star schema is a common dimensional modeling technique that organizes data into a central fact table surrounded by dimension tables. This structure enables efficient data querying and analysis, making it ideal for data warehousing and business intelligence applications. The snowflake schema extends the star schema by normalizing the dimension tables, creating a hierarchical structure. This approach can lead to more complex models, but can also improve query performance and flexibility for certain use cases. Fact tables contain the numeric, quantitative data that is the focus of analysis, such as sales figures, website clicks, or patient records. Fact tables link to dimension tables that provide context and descriptive information about the facts. Star schema is a type of dimensional data model with a central fact table connected to multiple dimension tables. This design emphasizes query performance and simplicity, making it well-suited for data warehousing and BI applications. Snowflake schema is an extension of the star schema, where the dimension tables are further normalized into multiple tables. This can result in a more complex model, but it offers increased flexibility and avoids data redundancy. Both star and snowflake schemas are commonly used in data warehousing to store and analyze large amounts of data from multiple sources. This enables powerful business intelligence and reporting capabilities. Fact tables are the core of a data warehouse, containing the key business metrics and measurements. They capture the quantitative data that is central to analysis and decision-making. Dimension tables provide the context and descriptive details that allow us to analyze the facts from different perspectives. By linking fact tables to dimension tables through keys, we can slice and dice the data to uncover rich, multidimensional insights about business performance. This powerful relationship between facts and dimensions is at the heart of how data warehouses enable deep, meaningful analysis. Data warehousing is about integrating data from multiple sources into a centralized, analytical repository. This gives organizations a unified view of their data to support data-driven decision-making. Effective data modeling, like dimensional modeling, is key to organizing data in a way that supports analytical queries and reporting. The ETL process, extract, transform, load, is crucial for getting data from source systems into the data warehouse in a consistent format. The ETL process is a fundamental part of data management and business intelligence. It involves 3 key steps: extraction, transformation, and loading. Extraction is the process of gathering data from various sources into a unified format. Transformation is where the data is cleaned, filtered, and prepared to fit the target data model. Loading is the final step, where the transformed data is loaded into a data store for analysis and reporting. Each of these steps is crucial for ensuring the data is accurate, consistent, and ready for use in decision-making. The ETL process is a powerful tool for organizations looking to leverage their data to drive insights and improve business outcomes. Effective queries are clear, concise, and precisely target the desired data. Use appropriate SQL syntax, table and column aliases, and meaningful variable names to enhance readability and maintainability. Optimizing query performance is crucial, especially for complex or frequently executed queries. Techniques like indexing, query simplification, and leveraging database-specific features can dramatically improve speed and efficiency. Queries often need to transform data in various ways, such as merging, filtering, or aggregating. Using appropriate SQL functions, joins, and subqueries can ensure the output data is in the desired format for analysis or reporting. Designing queries with reusability in mind, such as creating parameterized stored procedures or modular CTEs, can save time and promote consistency across the organization. SQL joins allow you to combine data from multiple tables based on a related column. This enables more complex and powerful queries that leverage data across your database. Subqueries are queries nested inside other queries. They let you use the results of one query as input to another. This allows for sophisticated data filtering and transformation. Properly using joins and subqueries is key to writing efficient, performant SQL queries. Understanding when to use each and how to structure them can dramatically improve the speed and accuracy of your data retrieval. The goal of this slide is to highlight 3 key best practices for effective data modeling. First, we emphasize the importance of establishing conceptual clarity, understanding the business requirements and domains before diving into the technical details of data modeling. This ensures the conceptual data model accurately represents the entities, relationships, and constraints. Next, we discuss the value of following normalization principles. Progressive normalization from 1NF to BCNF helps eliminate data redundancy and anomalies, leading to a robust and efficient data structure. Finally, we stress the importance of collaboration throughout the data modeling process. Engaging business stakeholders leads to better alignment between technical and functional requirements. These 3 best practices, conceptual clarity, normalization, and collaboration, form a solid foundation for successful data modeling initiatives. Data modeling is a critical part of building robust, scalable data systems, but it comes with its own set of challenges. As data volumes and sources grow, data models can become increasingly complex, making them difficult to design, maintain, and evolve over time. Scaling data models to meet the needs of large, enterprise-level applications is a common challenge that organizations must overcome. Business requirements and data needs are constantly in flux, requiring data models to be flexible and adaptable. Keeping data models aligned with shifting priorities and regulations can be a significant challenge for organizations. Ensuring data quality and consistency across disparate systems and sources is crucial, but often difficult to achieve. Establishing effective data governance policies and processes is key to overcoming data quality and consistency challenges. Capturing and representing the complex relationships between data entities can be a significant challenge, especially as models grow in size and complexity. Properly modeling these interdependencies is essential for maintaining data integrity within the organization. Data governance establishes the policies, standards, and processes to manage data as a strategic asset across the organization. This ensures data quality, security, and compliance are maintained. Data stewardship involves appointing individuals or teams responsible for overseeing specific data assets. Stewards ensure data is properly defined, secured, and used according to organizational policies. Successful data governance requires collaboration between IT, business units, and data experts. This promotes a shared understanding of data and its strategic importance to the organization. Agile data modeling is an iterative and incremental approach where the data model is continuously refined and expanded based on evolving business requirements. This allows for greater flexibility and responsiveness to changing needs. Agile data modeling encourages close collaboration between business stakeholders, data analysts, and IT teams. This cross-functional approach ensures the data model aligns with both technical feasibility and business objectives. Agile data modeling emphasizes validating the data model through iterative feedback loops. Stakeholders review and provide input on the model, enabling continuous improvement and refinement. Data modeling is a critical part of any data-driven project, helping to define the structure and relationships of data. There are a variety of specialized data modeling tools available, each with their own strengths and capabilities. Visio, Irwin, and Power Designer are examples of advanced data modeling software that provide rich visual diagramming, data lineage tracking, and model versioning. Relational database management systems like SQL Server, Oracle, and PostgreSQL also have built-in data modeling features to define database schema and enforce data integrity. For NoSQL databases, tools like MongoDB Compass and Couchbase Studio help visualize and manage the schemaless nature of document-oriented, key-value, and graph data models. Increasingly, cloud-based data modeling tools are emerging, like Azure Data Studio, AWS Glue, and Google Cloud Dataproc, which integrate with cloud data lakes and warehouses. Data models are not static. They need to be regularly reviewed and refined to stay aligned with changing business needs. Consistently evaluating the effectiveness of your data models is key. Look for areas where they may be falling short or could be improved. As your business evolves, your data requirements will change. Be proactive about updating your models to address these new needs. Optimizing your data models can help streamline data flows, eliminate redundancies, and enhance the overall efficiency of your data infrastructure. This iterative process of review, refinement, and optimization is essential for maintaining high-performing, business-aligned data models over time. The goal of this slide is to introduce the audience to real-world case studies that demonstrate the power and impact of effective data modeling. We'll be exploring how a leading e-commerce company used a well-designed data model to streamline their inventory management, customer profiling, and marketing analytics. By implementing a dimensional model with fact tables and dimension tables, the company was able to gain unprecedented visibility into their sales trends, customer behavior, and supply chain operations. This case study highlights how thoughtful data modeling can drive significant business benefits, even for large, complex organizations. I'll dive into the specifics of this e-commerce company's data model and the tangible results they achieved in the next few slides. Data modeling is a critical skill for any data professional. It allows us to design robust, scalable, and efficient data systems. Understanding different data model types, normalization principles, and best practices is key to mastering data modeling. Data modeling is an iterative process. Successful data teams continuously refine their models to adapt to changing business needs. Regularly reviewing and updating data models is essential for maintaining data integrity and unlocking new insights. Effective data modeling requires cross-functional collaboration between business stakeholders, data analysts, and IT teams. Aligning on data requirements and priorities through clear communication is crucial for delivering successful data modeling projects.